Alright, so let's go ahead and take a look at, I believe this is page 8 in the in our packet. Okay, so this first one here, and we're going to be using all these formulas for these problems. Remember the formulas, the ones that I'm going to highlight in yellow here, these ones can be used for up and down or a vertical direction. The other one that I'll throw in green here, this can only be used for our horizontal direction. Remember the reason that is? The reason that it is that this one and this one, both of these formulas here, they have to do with acceleration. Gravity's pulling us in the up and down direction, right? It's the thing that's accelerating us, whereas this formula, we don't have anything to do with an A for acceleration or a G for gravity. And remember, A and G can be used interchangeably. I could change this equation to that if I really wanted to. Change this equation over to A if I really wanted to there. Alright, so let's go ahead and take a look at the rest of the problems then. Alright, so number 11 here. We've got this plane, it's flying 75 meters per second, drops a package from 120 meters off the ground. So I already started diagramming that out. I know my plane is going 75 meters per second in this direction, therefore I'm going to draw a vector in that direction and label the vector as 75 meters per second. Careful, because the unit does matter here, since vectors can be represented in a variety of different units. Alright, my distance, notice I put y next to it just to kind of visually separate it and make sure that I know that this is distance in the y direction, because I could also have a distance in the x direction, and that's the thing that we're actually solving for, is the distance in the x direction. We're looking for that right there. How far did this package land from the initial dropping point? Okay, so for the first part of this problem, I know that I've got a distance in the y direction, and I know how much acceleration this package has. It's due to gravity, even though it doesn't tell me specifically what my gravitational attraction is or my acceleration is. We can assume we're doing the problem on Earth, so we're going to be using Earth's gravity of negative 9.8 meters per second squared. Why is it negative? Because gravity is always pulling us down. So that's where that negative is coming from, because again, gravity is pulling us down. Okay, so when we plug it into the distance equation, since I have a distance in the y direction, I can only go with components that are also in the y direction. So my initial velocity is not going to be 75. This 75, that's an initial velocity in the x direction. I need to be dealing with an initial velocity in the y direction though, but we know that. It's 0 meters per second squared. Or sorry, 0 meters per second. How do I know that? Because at first, before a person drops a package out of the plane, they're going to have the package in their hands at rest. It's going to be moving fast this way, 75 meters per second in the horizontal direction, but up and down, if the person hasn't dropped it yet, it's going 0 meters per second in the downwards or in the y direction. So our initial velocity in the y direction is 0 because it's not moving down, it's only moving horizontally. So not moving, so 0. I don't even necessarily need this part, right? Because 0 times anything is going to be 0. So it doesn't matter what my time is. It could be 1, it could be a billion. It's going to be times 0, so it's going to be 0 in the end. This part, you'll notice a little bit of a shortcut. Since gravitational acceleration is always negative 9.8 meters per second squared on Earth, and that's where we're doing all the problems, unless it tells us the moon, which we'll get into a couple problems here and there that have that. But for the most part, we can assume that we're at negative 9.8 meters per second squared times a half gives me negative 4.9. So you could almost just, instead of doing 1/2 times negative 9.8, just change the formula to negative 4.9 t squared, which makes it a little bit easier in terms of calculations. Not by much, but it saves you a little bit of time. A little bit of time here and there, though, adds up to quite a bit in the end. Okay, so this 0 is coming from what I just crossed out up here, plus negative 4.9 t squared. Well, I don't have t squared yet. That's what I'm looking for. So we've got to divide both sides by negative 4.9. If I do it to one side, I got to do it to the other. So that's what's going on in this step right here. And 120 divided by negative 4.9 gives me 24.49. Careful not to stop there, because a lot of people do end up stopping there and just realize we don't care about t squared, we care about t. So I need to take the square root, and I'm left with 4.95 seconds. Now let's realize what this 4.95 seconds represents. This 4.95 seconds represents my time in both the y direction and the x direction, right? Because it's my time. So however long it took the object to fall in this direction, in the vertical direction, well, it also took that same amount of time to fall in the horizontal direction. One object can't have two separate times. That's the variable that links all of our formulas, is time. Whether or not it's horizontal or vertical, it's going to be the same amount of time. So now I know my time that I was in the air for, 4.95 seconds. Well, since I know that, now I can solve how far horizontally the package went, right? Because my formula for horizontal distance is dx equals vt. Well, that's the same thing as v equals d over t. Remember, this formula, though, we can't use for vertical. We can only use it for horizontal, because horizontal is the only possibility where I may not have an acceleration. And in this case, if the plane was flying initially 75 meters per second and it doesn't accelerate in the horizontal direction, I stay at a constant 75 meters per second. So that's where the 75 is coming from, or I could do it over here as 75. I know my time from down here. That's what I plugged in right there. Or we could do it the other way, where it's dx equals vt. Realize it's the same formula, it's just rearranged differently for us. And then I would come out with dx equals 371.25 meters. Okay. Whether or not it's this way or this way, it's the same thing. So that's what this is right here. That bar right there, that horizontal distance, would be 371.25 meters in the dx direction, distance in the x direction. Okay. Number 12, man's driving 30 meters per second, slides off the edge of a 10-meter tall bridge. Okay, that's not too morbid. How far does he land from the bridge? Well, the bridge, here's my crappy drawing of a bridge, is up here. We know that it's 10 meters from the surface of the water. Well, how do we know how long it takes him to hit the water? It's always going to be dependent on the y direction, because gravity is the thing that's causing the acceleration. It's never going to, the time's never going to be dependent in the horizontal direction, unless I also know distance, right? Because then if I know a distance and a velocity, I can solve for it. But the thing that actually causes me to fall is gravity. So I'm almost always, I shouldn't say never, but almost always going to use the y direction to solve for my time. All right, so it's pretty much identical to the problem before. So it gives me a slightly different information, but the process is still the same. I've got my distance in the y direction, that's 10. My initial velocity at the top, it is 30 meters per second horizontally, but vertically, before he goes flying off the bridge, it's 0 meters per second. And think about your car driving down the road. You might be going really fast in the horizontal direction, but you're going 0 meters per second down, right? Otherwise you'd be moving through the road, or you'd be like jumping off the road or something like that. It'd be kind of crazy. So your vertical and horizontal speed is much different. So I'm trying to look for words here at 1 o'clock in the morning. All right, so the second half of this formula here, the 1/2 times negative 9.8, I told you guys already before, you can pretty much simplify that to negative 4.9 every time if we're dealing with gravity on Earth. All right, so from there, solve it algebraically. Nothing new here. 10 divided by negative 4.9 gives me 2.04. Take the square root of that, I get 1.43. Take that 1.43, stick it in here for the time, because I'm going to be using this formula for my horizontal distance. In this case, I don't know my distance, but I know that I was in the air for 1.43 seconds, both vertically and horizontally. I was in the air for 1.43 seconds. Doesn't matter which one I'm dealing with. Multiply that by 30, and I get my 42.9. All right. Moving on. The next one, It's pretty much the same process. We know it's the same bridge from before, so it's going to take 1.43 seconds for the object to hit the ground, in this case the car. Luckily, our guy makes it out alive because he's there explaining that he did not surpass the 15 meters per second speed limit, so don't worry, all is well, kids. So for the second part of this, I shouldn't say number two, the second part of this, we're going to be using the same formula that we did before. Velocity equals distance over time. Careful, because this 15 meters per second, that we're just comparing in the end. Once I get my answer, I'm comparing it to this, so don't end up actually sticking it into this formula. So my distance is 20 meters, because that's the known distance of the car. My known time is 1.43, so then I get a velocity of 13.99 meters per second. But usually this would be the answer, right? But it's not the answer. The answer is, was he telling the truth? Now, if the speed limit was 15 meters per second and he said he didn't go over the speed limit, he actually didn't. Mathematically, it supports that he was at 13.99 meters per second, which is not greater than 15 meters per second. So, yes, he is telling the truth. Good boy, not speeding. All right, next one. A man shot an arrow from 1.3 meters off the ground with a velocity of 21 meters per second. Remember, this velocity is, we're assuming, in the horizontal direction. So that's our V initial in the X direction. How far did the arrow travel? Pretty much the same as the previous problems in terms of how to work it. So just kind of refer back to those for the process. Number 15, a student flicked a pencil off a 1 meter tall desk and lands 1.6 meters from the edge of the desk. How fast did the pencil leave the desk? And these are actually accurate numbers. We did this experiment, or we will do this experiment, except not with a pencil. We'll be doing it with some projectile launchers, but this is the actual correct math for it. And that's what we try to do all the time, is as much as possible put physics problems into a real world perspective for you. So the desk is 1 meter tall. We know that. That's our dy. We know that the pencil goes 1.6 meters. That's our dx. If we know our time, we can link everything together. So that's what we need to solve for first. All right. So distance in the y direction, same process as all the previous problems. Plug everything in. Realize that our velocity in the y direction. I just realized I said x. It should be in the y direction. Is 0. Right? It's not going down at first. It's only going out. All right, so once I know my time, which ends up being 0.45 seconds after I do all the math, and again, the process is the same to the previous problems. Once I know that 0.45 seconds, and now I have something to plug in here. Right? The only difference between this problem and the previous couple problems that we just did is I don't know my velocity. The other ones I knew my velocity already. We're just working slightly backwards from what those were. I know that I'm in the air for 0.45 seconds, and I actually know my distance in this case. If I know my distance was 1.6, and I know my time of 0.45, well, I've got a distance, I've got a time. Remember, in the x direction, we're not going to be speeding up or slowing down because the only force acting on a projectile is gravity. So it's only going to be acting in the downwards direction. Well, this problem's dealing in the horizontal direction at this point. So that 3.5 meters per second after I do the math here, that's 3.5 meters per second here, also here, also here, also the split second before I hit the ground. It's constantly going 3.56 meters per second in the x direction until it hits the ground. We'll talk about that one quite a bit more in class. All right, for problem 16, there is a lot going on here. I realize that, and the other problems are very similar. So we got this football that's being kicked from the ground with a vertical velocity of 17.09 meters per second and a horizontal velocity of 15.4 meters per second. Let's go ahead and draw the scenario out. So just realize that we want to get to a point where we don't need to give you these sub-steps, like this A, this B, this C, the D. We would just say, how far down the field will the football land? Or what's the maximum height? And we would know, well, I probably should diagram it out. I need to figure out my time somehow, and then I can do these sorts of things. So Problem 16, 17, and a couple others are kind of just getting you in the habit of drawing those pictures out, drawing those diagrams out. Really, really important to do that. All right, even if it doesn't ask you. All right, so we know that our our vertical component is 17.09 meters per second, right? So that's our upwards direction, our y direction. We know that our horizontal velocity is 15.4 meters per second. So in our left to right velocity. And we may even want to make a note of that. This is our v initial x. This is my v initial, and I should put a y in there. All right, and it's going to give us this diagonal, kind of like we talked about in class. We get these diagonal movements because some of our velocity comes from the x direction, some of it comes from the y direction, so it's going to cause us to move in this diagonal. All right, so even though it doesn't tell me that my velocity is 0 meters per second at this point, it is. I know it's 0 meters per second because I'm at my maximum height. At my maximum height, this is where whatever object it is, in this case a football, stops for a split second to turn around. Remember, if it doesn't actually stop, it would just continue on and on and on forever until it got out into orbit. We know that's not happening, so it must have had to cross 0. If it's going from positive direction to a negative direction, it had to cross 0, right? So we know this always. Our maximum height is always, 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 always going to be 0 meters per second. Did I say always? Always 0 meters per second. All right, so our final velocity we know is just the reverse of whatever our initial velocity was. So if it was 17.09 meters per second up, well, it hits 0, and then by the time it falls back down, it gets to negative 17.09 meters per second. Our v initial x is going to be the same everywhere. It's going to be 15.4 meters per second, even in the middle. Over here, over here, over here at the end. Because remember, our initial velocity in the x direction, that remains constant throughout, so that becomes our velocity for everything. Since gravity's only acting in the y direction, there's nothing acting in the x direction, so our velocity is going to be constant in that direction. All right, so that's where I'm at here. I don't know my distance in the y direction. I still drew it in though and put the question mark, so I realized to myself, oh, later on I'm going to be looking for that. Same deal with the time. Time doesn't matter where it goes, right? Because it's independent of motion. Well, not entirely, but we're not going to get into that. So it can go anywhere. All right, so let's take a look at B. How much time did it take for the ball to land on the ground? Well, there's a couple of different formulas that have time in them, right? I know that my distance formula, right? Distance in the y direction equals v naught y t plus 1/2 a t squared. That has time in it, right? Velocity equals distance over time. That also has time in it. V minus v naught equals at. That also has time in it. But let's see how we actually narrow that down. How do I know that I'm not using one of these formulas over the other? Well, we don't know our distance and we don't know our time. So if I don't know both those variables, there's no way that I can solve the problem. Here, it's the same deal, except also realize that this one only deals in the x direction. Remember, our time is dependent on our y direction, though. So that one's out of the question automatically. That one should be the first thing to go. And then we realize, oh, well, I do have acceleration. Well, what's my acceleration? It doesn't tell me in the problem, but I know that it's acceleration from gravity, right? Gravity is negative 9.8 meters per second squared, so that's where I'm getting that negative 9.8 from over here. All right, well, I know my V final, it's negative 17.09. My V initial is 17.09. Go ahead and do the subtraction there. Divide it by negative 9.8 from gravity. And I'm just doing that because algebra would state in order to get t by itself, I need to divide by negative 9.8 since it's initially multiplied by that. Do it to one side, do it to the other. So then I come out with t equals 3.49. Now we've got to be careful. What does this 3.49 represent? Does it represent half my time? In some cases it will. Other times it will represent the entire time. Well, it's associated with my v final and my v initial. Well, my v initial is over here. My V final is over here, so that means my time is associated with this entire run. All right, so it leaves it as 3.49. The other way to do this problem is assume that we're just going from an initial velocity of 0 at the top here, not even have to deal with the front half of this, and only deal with this part. If I did that, I'd come out with a time of 1.74, but then I'd have to realize, oh, well, what does that 1.74 represent? It represents from where I had 0 velocity to where I had negative 17.09. Well, where was 0? Oh, it was halfway, so this is only half my time in that case. So a little bit more confusing way, but some people do like to do that. You'll see why in a little bit, but I would always recommend just going with the V final and the V initial, not dealing with the 0 in the middle. All right, so let's go ahead and take a look at the next one. What's the maximum height the football reached? Like I put here in the answer key, the maximum height, it is wherever I take half my amount of time. The reason that it's half the amount of time and not the full amount of time, so the reason I'm using 1.74 seconds here is because where is my maximum height? Oh, my maximum height is halfway through the flight. Well, halfway would be half the amount of time as well. So half the full amount of time would be half of 3.49, so 1.74, because it takes 1.74 seconds to get here to my maximum. I wouldn't use the full thing because the full amount of time would give me a height of 0, right? That's not my maximum height. That's my height right here at the end. Height at the top is the halfway point. All right, so I go to plug that into my distance in the y direction formula. Again, I'm using this formula because I get my maximum height, or I'm dependent on my time from the maximum height based on gravity, and gravity acts in the up and down direction. The only other distance formula I have is that dx equals vt, but remember, this formula doesn't have gravity associated with it. There's no g or there's no a, so that one's out of the question. Plug it in, it becomes a normal problem like the ones that we've done and talked about a million times before on how to do the math here, but we know that the initial velocity here is 0. The reason that I know the initial velocity is 0 because that's where I'm coming from my maximum height. Plug in our time, we end up getting our distance of 4.84 meters. How far down the field will the football land? Well, now we're talking how far down the field. Well, how far down the field, that gives me a connotation of from this point in the orange to this point over here. So that means I'm dealing with a horizontal direction. Well, since I'm dealing with a horizontal direction, I'm going to be using dx, because x, if we think of a graph, is in my horizontal direction, y is in my vertical direction. So I'm looking for horizontal. Remember, in my horizontal direction, whatever velocity I have to begin with, that's my velocity everywhere, since gravity is not acting in the horizontal direction. So that one's nice and easy. It's just multiply your horizontal velocity by your time. We just got to make sure it's the full time, because we're assuming it's asking us how far down the field will the football land. Well, it's not saying how far is it halfway through its flight. It's saying how far will it actually land. So when it hits the ground, that's the entire length of that travel. Okay. 17 is identical in terms of how we arrive at our solution. Right? First one, diagram it out. Second, in order to figure out your time, you're going to be dealing with anything that has acceleration in it, because gravity is the thing that's going to limit how long something's in the air for, or how much time it's in the air for. Maximum height, we're going to use half of the full time, again, because the halfway point is where I'm at my maximum height, and that's what it's asking me for. Do the math. How far does the long jumper travel? Well, if we're talking about how far, we're talking the full length, so I'm no longer using half my time, I'm using my full time there, and we're dealing with the x direction.